Great. Well, thank you all so much for joining us for the life cycle of a star. Have you ever wondered how stars form, or perhaps even how they die? After all, some of the most mysterious objects in the universe come from dying stars. Join us as we dive into the life cycles of stars, from their formation in massive nebulas to violent supernova explosions, black holes, and more. And this presentation is led by Caity Sullivan, who's a volunteer for the Solar System Ambassador Program through NASA's Jet Propulsion Laboratory. Caity also serves as an education associate at the Museum of Science's Charles Hayden Planetarium. So all of us, let's give a big virtual round of applause to Caity for joining us here today. And Caity, the floor is yours, and I'm going to spotlight you and hide my screen.
Awesome. All right. Hello, everyone. Let me put my camera on so you can see me. Hi, I am Caity, and as Robert already mentioned, I'm a Solar System Ambassador for NASA Volunteer Program, and I also work at the Museum of Science. So I kind of, my hobbies are also my job, which is very exciting, and I feel very lucky. So thank you all so much for coming. Super excited to be talking about this. Talking about the life cycles of stars is probably my favorite thing ever to talk about in the planetarium. So I'm really excited to share this with you. And as hopefully a lot of you know, the James Webb telescope, we just got the first pictures back from that telescope. And so I'll be sharing some of those because they wrap in quite nicely to the life cycles of stars, and a few other images as well, just because they're really pretty. So I'm going to be using a combination of software and animations that were created actually at the Charles Hayden Planetarium, as well as some images and animations from NASA itself. So there's going to be just kind of a whole bunch of different resources today. And the first one that I want to start with is a program called Worldwide Telescope. So this is a totally free and open source software. I think it only runs on PCs. I'm not sure about Macs, but you can download this if you want to, kind of play a video game. Essentially, that's kind of what it feels like. You're just traveling through the universe. You could go to different planets, and I really like to use it for virtual programs. It's kind of like being in a planetarium. So I have us starting here at Earth, which obviously is not a star, but I wanted to kind of set the scene and give some scale for where we are in the universe, where we are in our galaxy, and then, how far away are the stars that we are looking at in the nighttime sky, and where are all of these nebulas and star formation and supernovas and all this kind of stuff happening, like how far away are those events. So if we zoom out from the Earth, and let me just make sure I have changed over to that view. Okay, perfect. So this line around the Earth here, this is the moon, the orbit line of the moon. It orbits about 250,000 miles away from the Earth. And James Webb, and I apologize if you can hear museum loudspeaker announcements in the background, they should be finished soon. The James Webb telescope is orbiting about 4 times the distance that the moon is orbiting the Earth. So it's much farther out. It's about 1 million miles away from the Earth, well above Earth's atmosphere. So it's really able to peer very deep into our galaxy and into our universe as a whole. So other galaxies as well. So that's where the Webb is. And actually, before we continue, I want to just pause and show you a video of exactly how the Webb got to its spot in orbit, and tell you a little bit more about the Webb to give you some context for the images of stellar nurseries and planetary nebulas that we will see in just a moment. So this is an animation of basically the entire unfurling process of the Webb telescope. It was launched last Christmas, and it took about a month to get to its final place in space. And then it spent the next few months basically getting ready to take images. So what you're seeing right now is the sun shield unfurling, which is about the size of a tennis court. It's absolutely massive. So that take some time, and then it has to unfurl its mirrors. It has an incredibly massive array of mirrors. I think there are 18 hexagonal pieces to the mirror that are coated in beryllium, or they're made of beryllium and coated in gold. And it's, I think, just over 21 feet. So it's absolutely enormous. And that sun shield protects the telescope from heating up, basically. So it's always protecting it from the sun's heat. Even light reflected off the Earth, light reflected off the moon, it's protecting it from all of that so that temperatures on the telescope side can stay really, 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 really low. So this telescope is looking in infrared light. So if you think about the light that we can see with our eyes, that's actually just a very small part of the entire electromagnetic spectrum. We kind of have very puny eyes when you compare it to the entire spectrum. So James Webb is looking outside of what we can see with our eyes into the infrared part of the entire spectrum. So infrared light has longer wavelengths than visible light does. And so any kind of heat or added light can affect the observations done by the telescope. So it has to be kept very, very, very cool. All right, so I just wanted to give you a little bit of background on the Webb telescope, and we can zoom out now and look at our whole solar system. Again, for scale purposes. So right in the center here, we have the sun, which is the most massive object in our solar system. It's a star, right? But it's not a particularly like big or incredibly bright star when you compare it to other stars. It's actually a pretty average star, average in size, temperature, brightness. And actually we can go and give it a quick visit. Since we are talking about stars today, it makes sense to kind of start with our own here. So we'll fly up close to it. All right, here we are. Let's see if we can get even closer. There we go. So as I said, our sun is a very average star. It looks so big and bright in the sky because it's so close to us. It's about 93 million miles away or so, which I know sounds like a very long distance, but when we're talking about stars, that's actually very, very close by. The nearest star to our solar system, that's not the sun, is a star called Proxima Centauri, and it's about 4 light years away. So in space, we generally use, we describe distance in terms of how long it takes light to travel, just because if we were to use miles or kilometers, the numbers just get so big that it becomes really hard to kind of think about and visualize and manage. So a light year is the distance that light travels in 1 year. It's roughly 6 trillion miles. And as I mentioned, the nearest star to our solar system, that's not the sun, is 4 light years away. If we were to measure our distance to the sun in light time, Earth is 8 light minutes away from the sun. So that's a pretty big jump. And if we wanted to send anything out to that nearest star, like a spacecraft at current technologies, it would take over 70,000 years to actually send something to that other solar system, the closest one to ours. So that's why, we're not really sending things outside of our solar system. Some argue that the Voyager spacecraft have left our solar system, but they kind of left the influence or radiation of our sun, but they haven't left the gravitational influence of the sun. So they're still relatively close by. If they wanted to travel to that nearest solar system, it would still take them another 70,000 years to get there. So that kind of hopefully puts things into perspective here, but our sun is very average. If you could fill it up with Earths, kind of like a cookie jar, you could fit over 1 million Earths inside of it. It's really, really, really big. You could fit over 100 Earths across like the diameter. and then volume would be over 1 million Earths. And stars are made of mostly super, super hot ionized gas, which is actually a totally different state of matter called plasma. But you can think of it as gas that gets super, super heated and turns into plasma at these really intense temperatures. And so all stars are made of plasma, and mostly hydrogen and helium. But as you get closer to the core, sometimes there are heavier elements. And yeah, depending on the mass of the star. So our sun is mostly hydrogen and helium. And you'll notice that there are like little spots all around the surface and interesting kind of loops popping out, weird structures. That's all because of the sun's very chaotic magnetic field. Because stars are made of plasma and they rotate, they have very weird magnetic fields that kind of pop out the surface in these little loops, and it brings plasma along these loops. And sometimes those loops can snap, they get all tangled up and snap and send material out into space. And that's what we would call a solar flare. And on Earth in particular, if a solar flare is headed toward us, we can sometimes see the effects of that in the aurora borealis if you're far north, or in the aurora australis if you're closer to like the South Pole or very far south in the southern hemisphere. All right, so that's a little bit about our star, but now let's leave our solar system behind and take a look at some other ones. So of course, we don't need to worry about the laws of physics using this program. We don't need to wait 70,000 years to head to other solar systems. But I have kind of zoomed us back out. So now we are in interstellar space here. You may notice that some stars have different colors than others. They are kind of dim. There's so much space in between them that they just appear as these little tiny points of light. But they have all different colors. They come in different sizes, but they all form in a similar way. They all form in nebulas. So I'm gonna just switch us on over to this animation of a star birthing nebula. So there's all different kinds of nebulas in the universe. They are basically, I guess the most broad definition I could give you is that nebulas are just giant clouds, beautiful clouds of gas and dust in space. There are so many different kinds, and this particular one, as I've said already, is a star birthing nebula. And the reason that these types of nebulas are so good at forming stars is because they're cold and dense. And nebulas are mostly made of hydrogen and helium, the same stuff that comprises stars and a lot of gas giants. And really, most things in the universe are made of hydrogen and helium, the two most abundant elements in our universe. And so there's a lot of just cold gas and dust in these clouds, and that material tends to clump together pretty easily. And as a clump has more mass, so kind of think of it like a dust bunny, as a clump gets more mass, it also gets more gravity, a stronger force of gravity. And so then it keeps attracting more material, and eventually the clump gets so massive that it ends up collapsing under its own gravity. And so pressures and temperatures inside of the core of this clump, they skyrocket to the point where atoms, so like hydrogen atoms, are smashing together, forming slightly heavier elements like helium, and releasing energy at the same time. And this process is called nuclear fusion. And so we will view this nebula one more time because there are a few specific things that I would like to point out. All right, we're going to start that over one more time. So nebulas in general, especially star-birthing nebulas, they're absolutely enormous. Like this entire cloud is, dozens of, possibly hundreds of light years across. They kind of vary. And coming up here, kind of in the top left region, you'll see a star that has collapsed, or sorry, a clump of material that has collapsed it on itself. In that process of fusion, nuclear fusion has started inside the core, and that's what ignites and then fuels a star throughout its life. So that's just one star, but you can see there are many stars forming from this particular nebula. And solar systems, so there's a lot of material around these baby stars, a lot of which did not go into the making of the star itself. And so that material will kind of clump together and form planets and moons and asteroids and other things that you would find in a solar system. And these types of disks are called protoplanetary disks, and we will get up close to be able to see one of these. And since it has a lot of syllables in the name, we call them proplids for short. But as we come around the corner here, you can see an example of one of these proplids. So you can see the new star right in the middle, and then all of that material surrounding it. That is the disk that solar system objects come from. And then after that happens, if there's still any kind of leftover gas and dust, eventually, given enough time, it just gets kind of blown away from the star. The radiation from the star, it's called a stellar wind. It's not really a wind like we think of it, but just radiation kind of pushes all that material out into space. So when we look at our own sun, which is about halfway through its life, it's 4.5 billion years old, and it has another 4.5 billion years to go or so. So don't worry about canceling your weekend plans or anything like that. It's going to be here for a while. But because our sun is halfway through its life, it has already kind of blown away all of that extra material. And it has migrated away from the stars that would have also formed in the same nebula. I like to call them the sun's sibling stars, but they have migrated away and they don't call her right. So we don't necessarily know which stars are the sun's sibling stars. So one of the most fantastic images, probably my favorite image from the JWST, the James Webb Space Telescope, is of a star-forming nebula. So I can show you this image. It is absolutely stunning. This is a very small part of a much, much larger nebula. This is called the Carina Nebula, and this particular part is called the cosmic cliffs, for reasons that, seem kind of obvious. I don't know, kind of looks like a whole cliff structure. And if you went from one side to the other, that's about 12 light years across. And that's just a teeny, teeny, tiny part of the entire nebula, which is closer to like 230 light years across or so. But the detail in this image is just absolutely stunning. We can see lots and lots of brand new stars. The structures themselves, some of them can be light years tall. And they're all caused by radiation from stars within the nebula. So brand new stars that are emitting a whole bunch of energetic, very like ultraviolet light, and high energy radiation that's kind of carving out these cliffs. Now, what's really interesting about this particular nebula, so this nebula is visible in the southern hemisphere. You can't see it from up here in the north, but if you're ever in the southern hemisphere, you should be able to see this as kind of like a fuzzy part of the sky. Having a pair of binoculars or a strong backyard telescope would definitely help. You're not going to get anything close to what this looks like, but you should be able to see it in the southern sky. And this particular nebula is about 7,500 light years away from us. So this image is showing us what this nebula looked like 7,500 years ago, because it takes light time to travel through the universe. So that's something else that just absolutely fascinates me about, the universe in general, especially observational astronomy and telescopes that are looking really far out, is that we're quite literally seeing into the past. And telescopes are like the closest thing we have to time machines, which is a really cool thing to think about. So this is kind of a real life example of a star forming nebula. As I mentioned, there are different types of nebulas. This is just one kind. If we wait until the end of a star's life, we can start to see some more nebulas as well. So depending on the mass of a star, it will live for different amounts of time. And every star throughout the main part of its life is kind of this balance between pressure and gravity. So as a star is going through the fusion process in its core, converting lighter elements into heavier elements, it's releasing energy. And so it's creating this outward force of pressure that kind of keeps the star puffed up. And actually, I'm gonna zoom back into the sun just so that we have a nice visual of a star while we're talking about this. So we have the outer force of pressure keeping the star puffed up. That is being opposed by the inward force of gravity, because anything that has mass has gravity. And so these two forces for a star's life, those two forces are in balance. And so the star is not getting too big, and it's also not collapsing in on itself. And depending on the mass of the star, how much stuff it's made of, one of those two forces will kind of win out at the end of its life. So very small or low mass stars, things like red dwarfs, if you're really into different types of stars, that would be considered a low mass star. They are extremely fuel efficient. So they burn through their fuel very slowly. And so they can live for trillions of years, which is longer than the universe is old, which is wild to think about. Our universe is about 13.8 billion years old. So we've never seen a low mass star die. We have ideas about what would happen, but we've never actually observed that. Average stars like our sun here, they live for a few billion, maybe tens of billions of years. So our sun will eventually live for a total of about 10 billion years. And that generally is the case for average size stars. We've seen other ones die before, so we know what it looks like. And when an average star dies, when it runs out of fuel, I should say, because stars aren't technically alive, right? But they have life cycles. As they run out of fuel, pressure actually is the force that wins the battle with average size stars. And so you get a star that slowly expands and gets bigger and bigger and bigger in size, not mass. So it's just taking up more space, which means it's kind of more of a fluffy star. This is called a red giant phase. And eventually it just kind of sheds its outer layers of gas. And I like to call it like a very gentle, fluffy death, which is not the case for anything in space, but comparatively, it does seem to be kind of a nicer way to go, in my opinion. And I like to call these types of nebulas giant rainbow space bubbles for obvious reasons. That is not the technical term. They are called planetary nebulas. Nothing to do with planets. Sometimes astronomers can be kind of weird at naming things. But I think what actually happened was that someone saw one through a telescope and thought maybe because it was so colorful that it was a planet, but turns out it's a nebula. So the star, as it expands, it gradually sheds its outer layers of gas. And so you can see different layers here, the red being hydrogen. And as you get closer to the middle, there's blue, which would be oxygen. And right at the center there, you can see that bright object that looks like a star. That is the remaining core that is left over from the star. So there's no more fusion happening in that core. It's just extremely hot, extremely dense, and given enough time, will eventually cool off. So again, no more fusion happening there. And that's called a white dwarf. Don't know if I just said that, but yes, white dwarf. So this is eventually what will happen to our sun in about 4 to 5 billion years. It will get bigger, turn into a red giant star, and then just shed its outer layers and form a beautiful planetary nebula. James Webb Telescope also got an image of an actual planetary nebula in the sky, again, only visible from the southern hemisphere. It chose a lot of southern hemisphere targets. So you cannot see this from the northern hemisphere, and you just can't really see it at all in this detail, right? That's why we have JWST, but this is called the Southern Ring Nebula. We have a ring nebula up here in the northern hemisphere that you can see in the constellation of Lyra the Lyre. It's a very small constellation, but it's visible in the summertime. So if you have like an app, a phone app, and you're kind of looking for that particular constellation in the sky, it's part of the summer triangle. You can locate where the nebula is and then just grab some binoculars or a telescope, and you should be able to see a little fuzzy rainbow if you want to try observing that way. But this is the Southern Ring Nebula, so it's in a different constellation, and you can't see it from here in the northern hemisphere. But on the left, we have one picture taken by an instrument called NIRCam on JWST, and this particular instrument is looking in the shorter parts of the infrared spectrum. So if we think about what we can see with our eyes, the visual part of the spectrum, we can basically see from the shortest wavelengths, which is blue light, and then anything shorter than that gets into ultraviolet. We can't see that with our eyes, all the way to the longest wavelengths of the visible spectrum, which is red. So the shortest infrared wavelengths are just past red in the visual spectrum. And then there's a whole spectrum of infrared too, right? We've got the shorter infrared side and the longer wavelengths of the infrared side. And so the left picture here is the shorter infrared wavelengths, and the right side is the kind of more mid-range, medium-sized infrared wavelengths. So you can see that just by changing the wavelength, even if it's still in the same part of the spectrum, looking in different types of infrared light can reveal a lot of information. So on the left, we can see the incredible detail of the layers of gas that have been kind of thrust out into space. And so all of those oranges are, again, just like the animation that we saw, those are hydrogen gases, and then you get heavier elements as you get toward the core. And on the left side, you can see the white dwarf in the middle, but you can't really make out a whole lot of detail about that central core, but you can if you look in mid-range infrared wavelengths, which is the image on the right. The image on the right, if you look closely at the center there, you can see it's not just a white dwarf. There's actually another star in the middle there, and they're orbiting around each other. So you have the core of a dead star orbiting around a sun-like star, so a star kind of like ours, and they are in a binary system. And I don't think that there's ever been a planetary nebula that's been imaged well enough to be able to tell whether or not the central core is in a binary system. So this was really, really exciting. And you can actually take these two images and put them together so you get the full infrared picture, right? You get all the detail from the one on the left, and then you get the detail from the central region on the right. And so a lot of astronomy is kind of compositing images like that to show us the full picture. So this obviously was another one of my favorites. It's really hard to pick favorites with the images that have come from JWST. They're also incredible. So that's what happens to an average star when it runs out of fuel. Pressure wins the battle, it gets bigger, and then we get planetary nebulas. Extremely massive stars, so stars that are at least 8 times the mass of the sun, when they start to run out of fuel, gravity wins the battle. And so the entire star collapses in on itself, bounces off the core, and creates this massive shockwave that just travels through space in a huge, huge, huge explosion. And I can show you an example of one of these. So this is called a supernova. This particular star is a blue supergiant. So stars do have different colors. The blue ones are the most energetic, most massive. They are the gas guzzlers of the universe. But what you saw there was that star running out of fuel and collapsing in on itself. The core continues to collapse. It gets really dense. And so all of this material just bounces off the core and then hurtles through space at a very large fraction of the speed of light. And all that material that gets expelled during a supernova, that's where the heaviest elements form. So stars can form lots of elements up to about iron, but it can't fuse iron. But in a supernova, there's so much energy involved that elements past iron can form. And there are so many of those elements in our bodies that literally came from stars exploding. So when we talk about being part stardust or star stuff, that's literal. That's where a lot of the elements in our bodies and on our planet are all from exploding stars. And supernovas also leave behind nebulas, as you can imagine, with this kind of big cloud coming out. So I will show you a real image of they're called supernova remnants. And this is the Crab Nebula, probably one of the most famous supernova remnants out there. This is a Hubble telescope picture. And you can see like all of that material that is still moving through space. And right at the center there is the leftover core, which we'll talk about in just a minute, the leftover core of that star. And so this particular star, the star that created this Crab Nebula, exploded about 900 years ago. Humans observed it 900 years ago. It was Chinese astronomers actually that looked up at the sky and they were like, hey, that looks like a new star, because all of a sudden there was a really, really bright object in the sky. And so they were calling it a new star. And now when astronomers are looking at this part of the sky, they can see, oh, what they were seeing was a star exploding, getting really, really bright for a few days, maybe a few weeks, and then kind of slowly fading away. And so now we see this beautiful remnant left over. When a star goes supernova, I said the core doesn't explode outward, the core continues to collapse, and it can form one of two objects. It can turn into something called a neutron star, which looks something like this. A neutron star is a solid object that is insanely dense. So the object itself has the diameter of about a small city, of like the size of Boston. That's how big it is in size, but it has the mass of multiple times the mass of the sun. So if you were to take all that material in the sun times 2 or 3 and squish it down into a sphere with one side to the other of the sphere being the size of Boston, that is what a neutron star is. And they're incredibly dense. A lot of the times they spin and emit lots of electromagnetic radiation, as you can see in this animation here. And so when it's spinning and emitting a whole bunch of radiation, it is called a pulsar, which is the object at the center of the Crab Nebula. The star that left this behind turned into a spinning neutron star, or a pulsar. And so that's why we get all of the really brilliantly lit up structures. It's all from radiation from that pulsar. If you were to look at this image in a different wavelength of light, say X-ray, for example, you can actually see that pulsar because it's emitting really, really, really high energy light, at high energy radiation. And so X-ray is really, 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 really short wavelengths. It's the kind of opposite end of the spectrum as infrared and radio waves, those longer wavelengths are. So that's just one way, or one option for what the core of a star can turn into. The other one, and I bet you a lot of you are thinking of it already, the other one is a black hole. So black holes form when the core is so massive that it doesn't stop at the neutron star step. It just keeps collapsing in on itself until all of that material that makes up the core is collapsed into an infinitely small point called a singularity. It's very strange to think about, but what we're looking at in this animation is a black hole kind of eating up a star that's in orbit around it. Black holes are not giant space vacuums, even though they have an infinite amount of density. They still have like a measurable amount of stuff, right? So like if the core of the star was about 2 or 3 times the mass of our sun, we know that that's the amount of material that's been squished down into that little tiny point. So it has a measurable amount of stuff, which means it has a measurable amount of gravity. And we know that you can safely orbit around objects, massive objects, as long as you're far enough away and you're moving fast enough. You could think about it in our own solar system. The sun is not sucking in the Earth. The Earth isn't sucking in the moon. If you were to replace the sun with a black hole of the same mass, nothing would happen to the Earth. We would still be fine. We'd still be orbiting around it. We'd get very cold. We need the sun for other reasons besides its gravity. But our orbit would be fine. And as a matter of fact, we're all orbiting around a black hole in our galaxy. And it's not the same size as one of these black holes that just comes from a supernova. Those are called stellar mass black holes. These types of black holes are called supermassive black holes. And I can show you the location of the one that we are all orbiting, but we have to get really far out. So here we are. We have left our galaxy behind. We've never seen our galaxy from the outside. This would take a really, really long time to get anything out here. But we have a good idea of what it looks like because we can see other galaxies out there with telescopes and we can measure patterns of stars in our own. So we have a good idea of what it looks like. And this supermassive black hole is actually sitting right at the center of our Milky Way galaxy. It's called Sagittarius A star. And the way that black holes can get so massive is that material gets too close and it falls into the black hole, or it can collide with other black holes and gain mass that way. So there's a lot that can happen to have a black hole gain mass. And so eventually they turn into supermassive black holes. And the one at the center of our galaxy has the mass of over 4 million times the mass of the sun. So it's way more massive than our other black holes that just have a couple times the mass of the sun, right? And so everything at the center of our galaxy, there's a whole bunch of stars in the center of our galaxy, tens of millions of stars. And that's what gives that central region, that glow, is all those stars. It's kind of like the city part of the galaxy. And then our solar system is right at the crosshair of of what we're looking at. And so we're kind of like out in the suburbs. We're in the quieter areas of the galaxy. But in the center there, all of those stars are orbiting around the supermassive black hole. They're not falling in because they're moving fast enough and they are far enough away. So they're good to go. But yeah, they're all orbiting around it. And then that combined mass in the middle of our galaxy has enough gravity to allow everything in the rest of the galaxy to orbit around it. There's some dark matter thrown in there as well, but we're not going to get into that today. So without this supermassive black hole at the center of our galaxy, it probably would never have formed in the first place. We think that all massive galaxies need supermassive black holes to form and evolve over time. So they're actually extremely important to our universe. Without them, who knows, maybe nothing would exist. It's really wild to think about. And something really, really exciting that happened recently that maybe some of you caught on the news before James Webb kind of took over was the very first image of the supermassive black hole at the center of our galaxy, Sagittarius A star. And I have that I can put up here. It looks very fuzzy, but we have to realize that this object at the center of our galaxy is 26,000 light years away from where we are. And there's a lot of stuff in the way. So our galaxy, because when we're looking at the sky from Earth, we see the big cloudy band stretching across the sky if you're away from the city, right? And it's hard to see through all of that dust and gas. And so our telescope needs to see through all of that. It needs to be able to pick up light from a very dim source, 26,000 light years away. And in order to resolve something like that, in order to take a picture of something like that, you need an Earth-sized telescope, which of course, we don't have an actual Earth-sized telescope. So we simulate one by connecting all of these telescopes around the Earth. And so they're all imaging this part of the galaxy. And so we simulate an Earth-sized telescope, and this is the picture that we got, which is super, super exciting. That central dark area is the shadow of the black hole, and the bright areas around it is material that's actually orbiting around the black hole at almost the speed of light. So it's heating up around the black hole. And so that's why you kind of see those bright areas, and it's moving very, very quickly. The radius of the black hole itself is, and which the radius means the event horizon, or kind of the point of no return where light can't escape from that point forward. That radius is about the orbit of Mercury. So it's, a few tens of millions of miles. So it's actually, it's quite small for having the mass of over 4 million suns. But so exciting to actually have a picture of it. We really are in kind of a new era of astronomy, which is really exciting. At this point, I think I have gone a little bit over. So if anybody has any questions, I would love to take some.
So Katie, in the Q&A, Mike asks, what happens to the sun or a star in a binary system when it dies? And he did ask this a little bit ago. You may have addressed it, but why don't you address it again?
Yeah, so let me put back the Southern Ring Nebula picture so you can actually see the binary system on the right. So if one star, it's a really great question. If one star kind of sheds its outer layers of gas or whatever, and it's just the core that's left over, the other star is not impacted all that much. There might be some like material exchange, maybe some of the material that gets expelled from the star that's dying ends up adding to the other star, so that other star in the binary system might actually gain mass that way. But I don't think it would be like completely detrimental to that other star. Like I don't necessarily think it would trigger that star to, run out of fuel or anything like that. I think its composition might change a bit, its temperature might change a bit, but I think that's probably the extent of it.
Let's see, Nancy asks, how can fusion from the sun create energy on Earth? Not nuclear fission, but fusing. Hopefully I got that right, Nancy.
So I think, the fusion that's happening in our sun is releasing energy, right? And so that energy is in the form of radiation that gets emitted from the sun. And so those charged particles, that radiation that comes from the sun, it's directed in all directions outward from the sun. And so the Earth is within its kind of path of where all this material comes. And so, like, for example, the charged particles from the sun will get caught up in the Earth's magnetic field, travel to the field lines, and enter our atmosphere. And so in that way, we get these interactions that we see as the aurora. But that light, I mean, that's why the Earth is really just reflecting sunlight. So like when we think about the Earth, we've seen pictures of the Earth from space and one side is lit up. It's all just reflection from the sun. But that light, that radiation can be harvested and used as energy. We can kind of collect the radiation on Earth if you're thinking about like solar panels and things like that. So if you're talking about using fusion on Earth, like doing our own experiments, I think I don't believe we're there quite yet. It takes a lot of energy just to make things fuse. So I don't really know like where the balance is there. But I don't think we're close to getting fully fusion power on Earth, if that was the question. Yeah. I got to learn more about that.
Linda asks, what is the best source to see new photos from the Webb telescope?
Yeah, I think the best way, there is a website completely dedicated to the James Webb. It's run by NASA and ESA, and I can actually look it up to give you an actual URL. Let's see. Yeah, Webb. So it's web.nasa.gov. That is just all things James Webb. And I can put that into the chat for folks to use. And actually that was to just panelists. Here we go.
There you go. Yeah, sorry. Joyce asks, will there be more pictures from the Northern Hemisphere?
Yes, for sure. James Webb, these initial targets were chosen basically to test the abilities of James Webb. And so they were chosen very specifically because of, they have Hubble pictures of the same thing, so they can do comparisons. And they're just really beautiful targets. But yeah, there are plans to target many, many different objects all over the sky, including some in the Northern Hemisphere. And a lot of the targets will be chosen based on scientists' proposals. So scientists can actually say, hey, I want to observe this and do research on this, and they'll submit a proposal to the Space Telescope Science Institute, and they'll choose which ones they think are the best proposals. And so, whatever scientists are trying to look at, like that's what Webb is going to look at. Even targets in our own solar system, which are way more close by than we think about, like Webb's targets, but it'll be able to investigate our own solar system really well too.
So we're going to say last call for comments and questions. Next up is Joyce, who says, this has been fascinating. Caity did an excellent job making this complex information accessible. How does our understanding of Earth's position in the universe better inform us on how to address or mitigate the ongoing warming of Earth?
That's a really good question. Yeah, because I mean, I guess this is maybe more of a personal question or answer, I should say. But like, as far as we know, so far, we are we don't have evidence of life elsewhere in the universe. It is very likely that it exists, but it is probably so far away that we might not, at least in the next few hundred years, might not know about it. Maybe we will, but it would be so far away that like thinking about like other options besides our own planet is just like not really plausible. Like when we think about Mars as like a plan B, it would be, there's so much that would have to happen. So I really think that our place in the universe and learning about how far away everything else is, other galaxies, like just how in like hostile other places are, even in our own solar system, to life as we know it. It really makes me feel more connected to our planet. Like there is no other option. We know the science of climate change. We know exactly what's happening. We have the means to change it. And we just kind of have to come together and realize this is our place in the universe, and there's no other place. So we better take care of it and be kind to our planet, because it's a vast universe out there, and we're in it together. We're this little ball floating in space. We're all on it together. All humans that have ever existed have been on this planet. Our whole history is on this planet. Like we need to take care of it. That's my personal opinion.
And on this 95-degree day, and I know temperature is different than climate, but I think that's a good question to end on. One last comment from Nancy, who says, thank you. This has been a wonderful presentation. I would love to learn more. This was fascinating. Just a note, folks, our next session is going to be Wednesday, August 31st at 11 o'clock. Topic is NASA's most recent and next missions to the moon. So stay tuned for that one. Look for an email from me tomorrow with a feedback survey and a link to this recording. And Katie, do you have any last words before we wrap it up for the day?
Just want to say thank you all so much for joining, and thanks for your questions. This was a lot of fun.
Yeah, so thank you, Katie. Thank you to everyone watching at home. Thank you to the handful of libraries who helped promote today's talk for us. And we'll see hopefully many of you back in about 6 weeks on August 31st. So thank you all and have a great rest of your day. Bye-bye.